In this video, we're going to analyze the circuit known as the difference amplifier. It is this particular configuration of resistors, sources, and an ideal op-amp. And yes, we are using the ideal op-amp model here, which means we know that our currents coming in are zero. Now, unlike a lot of op-amp problems, we don't immediately know the positive or negative voltage. Neither one's hooked to the ground. Neither one's hooked up to a voltage source. So we are not going to be able to just use that to get our answer right away. We're going to set up some equations here. Now, if I look at this positive terminal, we have it labeled as VB. So then I can do my node voltage here. So I got three currents coming out of there. The current left would be voltage I'm currently at minus voltage I'm going to over R. Then the current going down, voltage I'm currently at minus voltage I'm going to over R. And then the current going right, well, ideal op-amp means the current going into the positive terminal is zero. It's going to be a little annoying to solve this, but we can do it. Multiply by R3, R4. That would get us an R4 VB minus R4 V2 plus R3 VB equals 0. We're going to go ahead and have VB here, then it's R4 plus R3 equals R4 V2. So VB is R4 V2 over R4 plus R3. And if you want to rewrite this here, we have essentially our scaling factor here times the input voltage V2. In fact, you could have done that easier if you'd realized that since there is no current going here, it's almost as if they're not connected. And this then becomes the voltage across this resistor. That's the voltage divider circuit. And hey, right there, that's the right answer for voltage divider. Now again, you didn't have to notice it that way and to solve it that way, but if you just do your node voltage, you will get the right answer anyways. Now, let's take a look at node voltage on the negative terminal. We've got VA listed there. So I would have voltage I'm at, VA, minus going left, V1 over R1. And then voltage I'm at, minus voltage I'm going to over the right there, V0 over R2. And then ideal op-amp, current going into the negative terminal is 0. We're going to go ahead and clear out our denominators here. R2 VA minus R2 V1 plus R1 VA minus R1 V0 equals 0. I'll go ahead and move the V0 by itself, and then the other side looks like I'd have R1 plus R2 times VA minus R2 V1. And so if I solve for V0 here, R1 plus R2 over R1 VA minus R2 over R1 V1. And we're almost done. This did solve for V0, but it solved for V0 in terms of VA, which is a value we don't really know. We know what V1 and V2 are here. However, by ideal op-amps, we know that the voltage on the negative is equal to the voltage on the positive, which means VA equals VB. So we can go ahead and substitute what VB is here into the VA down there. And we're going to get our final answer here, R1 plus R2 over R1 times R4 over R4 plus R3. All of this times V2 minus R2 over R1 V1. Now, if you chose your resistor values correctly, so choose R1, R2, R3, and 4 in a particular way, which I'll let you work out the details on that, you can get V0 is equal to V2 minus V1. So what that means is the output voltage here is exactly equal to the difference between the two input voltages with the one hooked to the positive side, V2 is positive, minus the other one, V1 there. So this is why it's called a difference amplifier, is because with this circuit, you can have it physically calculate the difference between two input voltages. You can have V2 minus V1. Now, obviously, we have a bunch of R's over here. So let's say, instead of wanting it to be V2 minus V1, what if you wanted to have like a weighted one where you say, I want 3 V2s minus only 2 V1s. Well, again, you can choose your resistors values to get that as well. So anytime you want to have some sort of multiples and subtracting of two numbers, you could build this circuit to do that for you. So this is a circuit that will calculate a certain algebraic expression. There is another one called the summing amplifier, where you have things hooked up a little bit differently, and the end result is the sum, the adding of the two input voltages. So you can do adding and you can do subtracting. There are other more complicated circuits, including ones where you can have it take derivative or integral. So we're going to eventually see how to build a circuit using an op-amp where the output is going to be the derivative or the integral of the input. So you essentially are going to be able to do calculus using op-amps here. This is just the most simplest operation we can do, subtracting two values, but you can kind of build your way up to more and more complicated expressions.